actually it's very sensitive one here, particularly. Yeah, these online classes and all, they're very sensitive. Sometimes, no, actually, you might have kept your mouse on that icon, and unknowingly, sometime actually it is pressed, and then it unmute may become mute, or mute become unmute and all. So then, like these these issues will come out actually with and some personal issues and all these things also will come out. Will be make it open and also very you should be very conscious and careful when you're using this online mode. Happens actually without our desire, things are happens and also, but you should be careful. Yeah. Okay. So yeah, here I just want to give you a break after this slide and all. So here, what I want to mention is that the data path or controller, whatever we have designed so far. So the same data path or controller we are using to execute or to perform the instructions for the entire instruction set. But as we observed that there are some instructions which will take very less amount of time, whereas other instructions which take longer amount of time. For example, as I mentioned, in case of load, it has to make use of all the data path components. So therefore, obviously it takes more time for performing its activity. Whereas in case of jump instructions, as we have seen, it's the other extreme, where it hardly uses any of the data component, just uses fetching and then address will be generated. Even it's not by using adder also, just by shifting the bits, it can prepare the address, and that address will be has to feed it to the PC. So there is a vast variation in the time that is required for implementation, but all of them use the same data path. So therefore, when you are using this data path for implementation, for designing a processor and all, you should have a clock cycle which can able to accommodate the instruction which takes the longest time, or the maximum time and all. So that's the way you have to design the clock, because here in this case, actually we are feeding the instruction by instruction and all. Like you are computing, you are fetching instruction and you are executing that, and then you are feeding, you are placing the next instruction to that. So every instruction has to be completed within a time. So for that purpose, that means for doing that, we need to have a clock. We need to have a clock cycle such that in one clock cycle, whatever the instruction will be, that all the instruction has to be executed completely. So for that, actually here, for in view of that particular design, we need to maintain a clock cycle such that even the worst case, the instruction which takes a longer time has to be satisfied, has to be completed within a clock cycle and all. So for that reason, if you design by that way, so those extreme instructions may be less, but by using a clock with a longer duration, so most of the other instructions which may take lesser amount of time, so there you are losing a time. That means even though they complete faster, but still as a clock time is clock duration is about whatever the specified, you need to wait till that time to fetch the next instruction and all. So that is the very major problem in case of the simpler approach, or this is also known to be single cycle approach, because here we are using one clock cycle for performing the entire instruction execution and all. Right. So that depends upon the clock duration, depends upon the critical path. Critical path means how many components are required to perform its execution and all. So whatever the instructions we have seen so far, the load instruction takes the maximum path. So what you can see, instruction memory, then register file, ALU, data memory, again register file and all. So therefore, it requires a larger time. So we need to design a clock to accommodate this one. Like this is the minimum clock time we have to choose. But with that, the other instructions will be affected. So that's what. So this is a simpler design. That means design of controller will be simpler and these things. But at the same time, when you try to analyze the performance and all, so the performance will be affected by using this. Because the only reason is that actually here it violates the principle of the common case faster. Common case faster. I'm not saying that the jump instruction is a common case and all, but there are other cases which requires less amount of time compared to the load, right? So they will be affected, like arithmetic instructions, for example. So they will be affected because arithmetic instructions are more frequent and all. right? So they will be affected because the load takes more time compared to that. So therefore, they will take a less amount of time. So therefore, we are not following the basic principle of common case fast. So with that, the performance issues will come into the picture. So the alternative or the solution to this will be a concept of pipelining, where we'll see that instead of using a single cycle, we can use a multi-cycle approach and all. We can use a multi-cycle approach. It means that, for example, load to visit all these things, assuming that each of them take one cycle. If you design a smaller clock cycle, it takes 5 cycles. Where in the jump instruction and all, it may take just only 2 cycles, fetching and then the decoding. That's all. And likewise, the different instructions will take a different cycle. So with that, you can able to optimize the time. So it's not a multi-cycle approach. So if you use the multi-cycle approach, then you can able to accommodate that nicely into the pipelining concept also. That means the multiple instructions can be operated or can be executed simultaneously on the same data path. We'll see the details of this pipelining and all in detail in the later and all. So now we can take a break just for 5 minutes, and afterwards you can come back and we'll continue what is meant by pipelining and what are the issues in that. So those things will continue that. So please take a break and then we'll meet after 5 minutes. Yeah. Hello. 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 Welcome back.
Yeah, yes, sir.
Yeah, right. Right. So, any questions? Anything? Okay. So far, we discussed about the simple way of designing a processor using a single cycle approach. So the idea is that having the same data path and a controller with which you can able to like implement the instructions. But here the crucial thing here is that the instructions will be executed one after another. That means the instruction is for the first instruction is fetched, and after completion, then only the next instruction will be fetched, and then it will go. Then it will go for execution. So likewise here, the instruction by instruction execution will be done sequentially or serially after completing the every instruction and all. So whereas the concept of pipelining is a little bit different. So here also the instructions are executed sequentially, but they can able to place the multiple instructions simultaneously where different instructions will execute different parts of the database or different components of the database so that you can effectively utilize the even the the data path components also. Whereas earlier you have same data path will be there, and until the completion of instruction you are not using the other you are not, that means here for example you have ALU will be there, so ALU functionality may take actual maybe around 200 nanoseconds, right? But throughout the instruction execution, but that is occupied. You cannot use it for some other instruction, or there is no way that you can use the ALU for some other activity and all. So for the entire instruction execution time, so all the elements, all the data path elements, all the data path components will be occupied, right? Even though their actual time for performing their operation may be limited, maybe less, much lesser compared to total instruction execution time, but still they are forced to occupy it with the same instruction and all. Whereas in case of pipelining, we'll try to split that. We'll try to divide that, and then we'll try to effectively utilize these data path components by the multiple instructions and all. But at any time, only one instruction will utilize the each data path element, but the data path elements will be effectively utilized in case of the concept of pipelining and all. So that we'll see here now how it happens and all. And for this, you can take any real world, several examples you can visualize. You can take it and you can visualize over here and now. And here in this context, the example that was considered here is like a laundry system and having a washing machine, dryer, then after the after no, after this is a kind of the sequence will be something like that. We have the blue colored one is the washing machine, then the dryer maybe, then afterwards you are folding the whatever the clothes or whatever properly, and then these folded clothes will be properly placed in the some storage, some almirah or whatever. So these are the four stages. Like the task here is that we have dirty clothes and then cleaning them everything and placing them in a properly then almirah. So this was the task, and this task, if you can effectively visualize as different subparts like washing machine, first washing, then afterwards drying, then afterwards properly folding back, then moving back to the almirah, placing in the almirah, storing in the almirah. So if you make them as a four distinct subtasks, and we can do that parallel. That means we can do that in a pipelined way. It means that first you will place a load of clothes here, and once the washing is over, then we'll take out, we'll place it in the dryer. Then the washer will be free. So in that case, you can place another load, and then when the dryer is over, then you go into this folding one, and then the dryer is free. At that time, if the washing of the previous if the following one is over, then you can place it over here. Likewise, the pipeline, the stages are like will be occupied all the time, and here the number of loads that will be carried out, that will be like washed or cleaned up, will be much higher compared to this is a non-pipeline fashion. Whatever is here is shown in the top figure, where even though we have a task, that means that means the tasks are placed, the tasks are executed the way it's a non-pipeline one. Non-pipeline one, the method what we discussed so far just earlier. It means that first you give a load and you have to wait till completion of the load. That means you place the clean clothes into Almara. Then you take the second load. Then you do it. Then take the third load complete. So when you do this way, you can say that for cleaning the four loads, for example, four tasks, you require a time of this much. Like each of them takes a 3 hours or 4 hours, for example, it takes about 12 hours because whereas if you make it in a pipeline fashion, then you can able to finish the task of these four loads in a time of like 1, 2, 3 and a half hours itself. In the time of 3.5 hours itself, right? So that way, if you try to analyze the performance improvement when you're for this particular simple toy example, you can see that it takes 8 hours here over here, and whereas here it takes only 3.5 hours, right? So the performance improvement will be like order of 2.3 in this simple case itself. In this simple case, and suppose if you make it like a bigger one, like for example, instead of just four loads considering, if you consider huge large amount of loads, like many loads, then in that case you can able to see the performance improvement will be much higher, like order of 4 or something like that, right? So that depends upon the number of pipeline stages and all, like how many stages are there. So that much improvement you can able to attribute to that. If the number of inputs or the number of tasks, if you take statistically a larger number, so in that case, the improvement in the performance is nothing but just the number of stages. And for that, to just like if you use this analogy or this make use of that idea in the implementation of MIPS architecture, ISA on the processor and all. So then you can view this the MIPS instruction execution as 5 different stages and all, where instruction fetch is nothing but just fetching the instruction from memory, instruction memory, and instruction decoding and the register read. So both can be done in the same stage itself. It means once the instruction is fetched and the same instruction will be given as input to the decoder is nothing but the controller, and also from the instruction word itself we'll come to know that what are the register operands, whatever. So from the register operands the data will be fetched automatically and then make it available at the read port. And then afterwards the execution part, execution phase, where so from the register operands or whatever is there that are available, so that on those operands the execution can be performed either for calculation of address or for performing arithmetic operation, whatever. And then the memory access can be done. If it is a memory access instructions load and store, then the memory access can be done either for storing the data into memory or fetching a data from a memory. And then another operation will be write back. So write back is nothing but like after fetching a data from a memory, again place it into one of the registers, or maybe in case of R format instructions, after the execution phase, right? Then you have to place the data into the register file. So that way overall, when you look at, so if you look at this way, in case of R format, the memory access is not required, right? And in case of store instruction, for example, then the write back stage is not required. So likewise, but to accommodate all the instructions and all, so we need to design a pipeline, or we need to have we need to consider all these 5 stages and all. So among these 5 stages, the first two stages are common. The first 2 stages will be same for all the instructions and all. You need to fetch an instruction that is required, and afterwards you need to inspect or you need to decode the instruction. What is this and all, what operation to be performed, that task has to be carried. So therefore the first 2 tasks are same, and the others and all that depends upon the instruction and all. Yeah, this is just an example to just convince ourselves that actually how the pipeline will enhance the performance compared to the non-pipeline and all. And anyway, I'm not going to this one because this is a numerical example and this is very intuitive, like as we have seen and as we come across in the day-to-day life in several instances or the several tasks that you can able to perform in a pipeline way, or you can perform in the other way also. So we can notice or you can see the difference how it used to be. The same thing here itself illustrated with the appropriate example and all. Like you can see here these things. And the thing here is that actually suppose these are the various instructions and we know that these are various data path components that are involved by the various instructions and all. And if you use a single cycle approach, then these different instructions will take a different amounts of time, needs different amounts of time. Like for example, load instruction, it needs 800 picoseconds, whereas a store word, it requires 700 picoseconds. So likewise, R format and other things and all, it requires that much amount of time and all. So so for designing the processor, in this case, by using a single cycle approach, our cycle period should be 800 picoseconds because the load word, this particular instruction takes a maximum amount of time. So therefore, the clock time, or you can say that clock period, the cycle period will be 800 picoseconds should be there if it is a single cycle approach. And suppose if you want to design using a pipelined approach, where you consider that the different stages in a pipeline are like this for these 5 stages and all, like instruction fetching, and then the register read are nothing but instruction decoding, both are together. Then the ALU operation, that's nothing but execution stage. Then the memory access, then the write back and all. So each of them will have their own timings and all. And but when you want to design the pipeline, so all stages should have the uniform time. All stages should have the uniform time. Otherwise, we have the inconsistency, and then you have a problem because if you make some stages faster and all, because you have to use this, you have to implement this using a multi-cycle clock, or again you have to use it like using a clock. That means with respect to clock only, these has to be these operations are these individual stages has to be activated, has to be run. So if we have a different time periods and all, then it will be difficult. You cannot accommodate that with a specific clock and all. So therefore here, even though if you see that out of these 5 stages, 2 stages require like 100 picoseconds and the remaining requires 200 picoseconds. So if you want to design by using a pipeline one, then you have to go for a clock with a 200 picoseconds. You have to go with a clock with a 200 picoseconds where each stage will be uniformly done. And so at some stages and all you will be losing. But so that's the reason that actually when you are going for a pipeline, you have to see that, or when you're designing the pipeline, that all the stages are more or less will be taking the uniform amount of time, so that it leads to the optimal performance. Okay, so based on this, if you go by this way, using the previous table as per the numericals in the previous table, if you go by pipeline and all, if you go by normal single cycle approach, right? Normal single cycle approach, you require because you need to design with a load instruction, so therefore all the instructions will take 800 picoseconds. So that way, this is the way the pipeline will go on. This is the way the non-pipeline structure of execution will go on like this. Like everything will be 800 milliseconds and all. Suppose if you do it with the pipeline one, then you can see that because you splitted that into the 5 different stages and all. So at each stage or for every stage, you can able to enter the new instruction and all. Suppose you start from here. After the first stage, now this stage is free, instruction fetch is free. So therefore you can fetch the next instruction. Then once this is completed, then you can fetch the next instruction. So that way you can fetch the instructions like for every pipeline duration, stage duration, whatever is there. For every that quantum, you can able to pick up the new instruction, you can feed into the pipeline. And then the instructions will be executed sequentially. Sequentially means like passes through the pipeline stages one after another. And so that you can see that the overall the throughput will be something like for every pipeline duration, stage duration, you can able to feed a new instruction into that, right? Whereas here and all, after completing the instruction only, you have to feed you can able to enter the new instruction and all. So that way, if you take a larger number of instructions, suppose if you want to execute some a code of like 10,000 lines or like 1 lakh lines and all, at that time, when you look at that, so this one, the non-pipeline concept or without pipeline stages and if you perform the task, then it requires about 800 picoseconds multiplied by the number of tasks, whatever is there. Whereas here, if you see that you are feeding the task for every 200 picoseconds, right? So therefore, if you see the performance difference and all, you can able to see that almost by using a pipeline here, you are achieving a performance of like order of 4 times better compared to the previous one, right? Compared to this one, because it requires 800 picoseconds for completion of single instruction. Whereas here and all in the throughput level, when you see that for completion of instruction, for every 200 picoseconds, you are feeding a new instruction, right? But if you look at here also each instruction will take this amount all by because an instruction to complete, the instruction has to visit all the stages, right? Here in this case, it may take about there are 5 stages. That means at the end of when you feed the first instruction, then at the end of 1000 picoseconds, it may give the first instruction will be properly completed. The second one, likewise. But when you look at the overall, that means in a bigger program, when you look at that, so you can able to see that the last instruction will be completed after it feeded by this one, this small that means additional 800 picoseconds is required. That means it will the tasks are completed one after another with a slight delay of like the pipeline delay and all. But if you look at that in the overall, like when a number of instructions to be executed in a very larger sense, then you can able to see a factor of like whatever. Here it's 800 picoseconds, it's a 200 for every instruction you are feeding. So almost like a 4 times improvement, you can able to see that, right? So the same thing here also, we are just I think whatever I just mentioned here you can see. Here what I'm saying is that you are not when you're using pipeline concept also, the latency is not changed. Latency means the instruction execution time, the execution time per instruction, that is not changing at all. But here you are staggering the instruction or you are mixing up the instructions in a nice way in a pipeline stages. So with that actually you are getting the better performance at all. So you can see that latency does not change at all, does not decrease. Latency means the the computation time per instruction or like execution time per instruction. So that remains same. That remains same. But the only thing is that since the throughput is here very high, so with that you are getting a better performance and all. Whereas in the case of non-pipeline structure, the throughput is less. Throughput is less because after you complete execution, then only you have to feed the next instruction. So that way, the performance is much better in case of the pipeline approach and all. Right. So we'll see that the details and all later on actually. So when you want to, in case of pipelining, with respect to the designing of instruction set architecture. So if you look at the MIPS architecture is very much friendly with the like a pipelining for designing the pipelining concept and all, or a pipelining approach for if you want to design a processor or if you want to pipeline instructions and all. The MIPS supports a lot. So by using these particular features and all, you can see that in case of MIPS, all instructions are 32 bits. It means that there is some consistency, some regularity and all. So with that, since it is 32 bits, you can able to place all the instructions in a properly in a word format at a word level addresses and all. And you can fetch them easily and you can also decode them easily because all instructions are 32 bits. And then they are limited to very few formats, as we have seen the R format and I format and the jump format and all, only few formats. So with that, even the designing the decoder is also simpler. Decoding is easier, and the decoder circuit also will be simpler. So that way, the MIPS architecture, whatever, it just provides because of 32 bits, it is easier. And whereas if you look at the other instruction set architecture, which supports like this x86 series of chips and all, where the instructions are widely varying. The length of the instructions are widely varying, starting from like it varies from 1 byte to 17 bytes and all. So in these cases, if you want to use the pipeline or if you want to perform any decoding and all, so it is very hard because where the instruction lengths are different and then the complexity in the decoding will be very high, very higher orders and all. So therefore, what they do is that actually even though the instruction architecture supports these variable length instructions. And again, there will be kind of again a translator where it translates these variable length instructions into the uniform length, some simpler instructions like kind of MIPS instructions and all. Then those MIPS instructions, those simpler instructions are used for pipelining and all. It means what I mean to say is that x86 and all the actual instruction set is widely varying, like 1 to 17 bytes of length and all. And if you directly want to use it for pipelining, or if you want to design a processor with this, means it is complex. So to simplify this or to make it more efficient, so there will be another layer of translation of instructions from these variable lengths to the simpler instruction set, simpler instructions which contains very simple operations and more or less uniform kind of a thing. So if then upon using those simple instructions, we can design the pipeline. So that way, we can if we want to use the pipeline and all, then the architecture should support the underlying the design of the pipeline or hardware and all. So here the regular info, and again, as I mentioned, 32 bits, it is somewhat regularity. And another thing, the number of formats also very limited, as we have seen in the previous lecture. I have mentioned that. I gave the formats. I have mentioned that like you have opcode for everything. Opcode will be there, the most significant 6 bits. Then following the opcode, the 5 bits will be like all the time it will be register contents and all. And the next will be like the second operand, and the destination will be there. There are few variations will be there. Otherwise, more or less it is very regular. And with that, the designing the decoder and the other things will be easier and all. So the same thing here, as I already mentioned, alignment of memory operands and these things. So what I mean to say is that actually the MIPS architecture is very much friendly, or it supports nicely for the pipeline architectures, designing the pipeline stages. Yeah, the next one is that when you are using pipelines, as we have seen, it appears to be like the pipelines will provide you the better performance, or like the optimal performance. But there, as long as the pipeline, the instructions in the pipeline, they go smoothly, like without any issues at all, then can able to see the performance achievement, like whatever the number of stages. But it's not true all the time. Right? There are certain issues will be there, like when you are implementing the pipelining and all, where there will be issues where you cannot feed the next instruction immediately after the stage crosses and all. After a particular instruction process, you cannot use the next instruction immediately, right? There are some certain problems will be there. So those problems are broadly categorized into these 3 categories, known to be structural hazards, data hazards, and control hazards and all. So we'll see that each of them, what it means here and all. So here structural hazard means basically, suppose we have a resource, and that particular resource will be busy by some other instruction, but the same resource has to be used by the next following instruction also, for example. So what it means is that the required resource by a particular instruction at a stage is busy by occupied by some other instruction and all. So that means there is a conflict. It means we have this resource, and the same resource is required by the multiple instructions, because in the pipeline you have multiple instructions will be there at any point of a time. You have multiple instructions that depends upon number of stages and all. So there may be a cases sometimes a particular resource may be required by the multiple instructions. For example, you have a load instructions where you have to write into the register, right? And then at the same time, some other register also, some other also needs to use that register file and all. So there will be a conflict. That the same register file has to be used by the 2 instructions. Sometimes you can use that effectively, because load means it has to write into that, whereas the other instructions may read from that. So that may happen. That can be done properly if you do it. But sometimes, suppose for example, you have only one memory was there instead of data memory and instruction memory separately. For example, assuming that you design a system with only one memory, where that memory takes care of both the instructions are there, data were there, both were there in the same memory. So then if you use a pipelining and all, then you have a problem, because the same memory has to be used At the fetching stage, instruction is required to read the instruction from that. And then after some stage, maybe load and store instructions, they need to fetch the data from that, or they need to write something into the memory also. So maybe there may be instances will come that actually simultaneously the load instruction has to read from the data, and again some other instruction has to fetch the instruction also. So there the conflict will be there, and such problems are known to be like structural hazards and all. This is mainly due to the resources whatever that are used, or the data paths that are used will be like required by the multiple instructions simultaneously. That's where the problem arises and all. So one way to overcome this is that, so you need to avoid that. That means instead of using, as I mentioned, suppose the memory, if it required by both load and some other instruction, then in that case, don't use the single memory and all. You can use the multiple memories, like two memories. So one is meant for instructions, where it holds only instructions, and from that you can only fetch the instructions. And if you use some other memory where the data will be kept there, you can read or write into that. So that way, that particular hurdle or particular hazard can be overcome by providing the desired resources, the required number of resources and all. Then the data hazard, it means that here the data hazard here means in the process of execution of instructions, one instruction may require a data from its previous instruction. That means outcome of a previous instruction. That means because here in the pipeline the instructions are executed, or the execution is going on in a sequential way, like stage by stage and all. And at a particular point, one instruction needs to read the data, where the data to be read will be the output of the previous instruction. And then the output of previous instruction is not available by that time it wants to read the data. Then there will be a conflict. It wants to read the data, but the data is not available at all, because the data has to be right back into the register by its previous instruction, but that not yet completed. So such hazards are known to be like data hazards. So it is basically due to the dependency on the instructions, dependency of the successive instructions done. Like the instruction I requires the completion of the I-1 or I-2 and all. Unless the I-1 is completed, then the I instruction at a particular stage is stuck there. It requires the data from the instruction from the I-1 and all. So such problems are known to be the data hazards. This is basically due to the dependencies across the instructions that used to be there as a part of the program and all. So we'll see that how to overcome this. So one way is that actually, if it is possible, when you're writing the code or the assembler, if it sees that there is a dependency in a very successive instructions and all, if possible, you can separate them. You can push some other instructions into that without creating any harm, without creating any errors in the final result and all. You can able to place some other instructions so that the dependencies can be overcome to some extent. So that is from a software side, as a programmer can do it, or the assembler can, or the compiler can, a clever compiler can able to do that. If it is, but it's not all the time, it may not be possible and all. So that way, there's one way is that actually you can able to like reallocate, or can able to like change the sequence of the instructions and all. So that way you can do it. And other way is that we'll see that what can be done in the other ways. And there is another one known to be control hazard. So control hazard means here from the name itself. So like when the program is in the execution, usually the program instructions will be executed sequentially, like one after another in a sequential order. Sometimes based on instruction, as we have seen in the conditional instructions, conditional jump and so on, conditional branches, where the instruction to be executed, the next instruction to be executed depends on the condition. Depends on the condition. If the condition holds good, then the control will go to some other instruction. If the condition doesn't meet, then the following instruction will be executed. So in that case, also here we have a problem, because in case of normal pipelining, the instructions will be like fetched sequentially, one after another and all. But if it is a branch instruction, we will come to know the branch result, or you can come to know the condition of the branch, whether the branch is valid or whether the condition holds good or not. That will be known only the third stage. But prior to that, we don't know. So therefore, Prior to that, the instructions following the branch will be simply inserted into the pipeline. And when you come to know about the branch result, if the branch doesn't happen, no problem, because the following instructions will be executed. Suppose if the branch is true, that means if the branch condition satisfied, then the instruction to be executed is not the immediately following instruction. The instruction to be executed will be slightly away from the current instruction, right? More away from the current instruction. So in that case, we have a problem. That means whatever the instructions that are feeded soon after the branch, and so those has to be again nullified. Those has to be again flushed out. So those are the problems with the particularly like when you are inputting instructions and all. So what will be the next instruction? So that for that, in view of that, you have problems that are associated with the control hazards. So sorry, basically the branch instructions and all, and those problems can be viewed as a control hazards and all. Whereas these control hazards, data hazards, all these things, they doesn't appear in case of single cycle approach, right? In case of single cycle approach, you don't have any problem at all, because the instructions will be executed like one after another. After completing the first instruction, then the next instruction will be starts its execution, or fetching and starts its execution. So that way, these kind of control or data hazards you don't observe, you don't find in the normal single cycle approach or simplistic approach. So we'll see that how these hazards can be handled and all. Yeah, as I already mentioned, like in case of structural hazard, it is due to the conflict in use of resource. I gave the example, the same example here also there. In case of MIPS, if you use the single memory and also, then we have a conflict like load and the other instruction. Like, because the every cycle you need to fetch a new instruction. That means you need to fetch the memory and all. And also there are some other instructions like load, store, and other things. They also need to access the memory. So then there will be a conflict. So that means, suppose for example, your first instruction is the load, right? And then afterwards you have the following some instructions are there. Then when the load reaches to the fourth stage, it's nothing but it's a memory stage, right? After computing the execution, after computing the address, then it has to fetch the data from the memory. So in the fourth stage, the load instruction requires to access the memory. And at the same stage, every stage, the instruction has to be fetched. The new instruction has to be fetched. So there is a conflict there and all. Whether that means it provides the two addresses and all, from that which instruction, which task has to be carried out. There will be a conflict, right? So there is a problem there. So that is going to be a structural hazard. So one way to handle that problem is that actually, like the instruction fetch would has to be stalled. That means when the load instruction, if you want to use only one memory and all, so at that time, what you need to, when the load reaches to the fourth stage, at that time, you should not fetch the new instruction. You had to use the memory for fetching the data from the memory and all. Then once it is completed, then you can fetch the next instruction. So during that time, what happens when the load is using that memory, but you are not fetching the new instruction. So therefore, there is a gap in the pipeline. So that is known to be a bubble. Like it's not a continuous flow. There is some vacuum. That vacuum is due to because of the resource crunch, because of the only one resource that is required by the two instructions sender. So we are giving access to only one instruction. So therefore, other instruction has to be do nothing. So there won't be any fetching at all during that time. So therefore, there is empty space in that particular stage, and that empty stage will be percolated, like propagate through the entire the sequence and all. So this way is known to be like a bubble and all. It means that sometimes the no operation has to be incorporated. That means during that stage, that particular instruction should not perform anything at all, right? So this is the problem with the structural hazard. So we can able to overcome this by using that, by providing. That is the reason that in the case of pipeline architectures, we have shown that two memories are. One is the instruction memory, other is the data memory, right? So that way, the structural hazards you can able to overcome by devoting the sufficient resources, so that you don't have the hazard at all. You don't have any problem with the resources. Okay. So next one is the data hazards. As I already mentioned very briefly, data hazard usually occur because of the dependency between the instructions and all. So if you look at here, this particular sequence of instructions, for example, you have add instruction first and then followed by the subtract. excuse me, subtract instruction. So here in case of add instruction, the result will be there in S0, right? It means that you perform addition between these two register contents, the result will be placed in S0. So here, when you to perform this one, the add instruction, if you see this is a five stage pipeline, and if you look at the way the pipeline execution will be represented for this way, you have 5 stages. This is IF means actually instruction fetch stage, like that means from the PC address you will fetch the instruction. Then afterwards, this is going to be instruction decoding and register content access also. So this is the second stage, instruction decoding or the register contents access. Then the third stage is that execution, like ALU execution or whatever. And the fourth stage is that memory access, right? And the fifth stage is that write back and all. So that way, these are the 5 stages in a pipeline or 5 stages of instruction execution. And depending on the instruction, some stage may be skipped or some stage, that means in some stage there won't be any activity at all, right? For example, in case of add instruction, the instruction fetch and decode will be there for all instructions, as I already mentioned, right? And execution will be done on these 2 operands, T0 and T1, right? T0 and T1, they are available, and it will be done in the execution stage. Then the output of that sum, the T0 plus T1 is available here. But in the next stage is the memory stage. So we have nothing to do with this. In this particular instruction, the output will be placed into the register file. So the memory stage will be like it is just simply passing the time. That means whatever the output is there, just this output will be fed to the this one, the write back will be right into the register file and all. So during this memory stage, this particular instruction will do nothing. It will not do anything at all. So that's why just for showing purpose, actually you can see that this particular block is shown as white. It means that there is no activity here at all, right? And then it will be the next stage will be write back. So we are writing back into the register file and all, right? And again here, if you see the convention here and all, for writing, we are just showing that half of the time is showing as shaded color. And whereas in case of reading, the half of that, the later half, the second half is showed as a shaded one. Because actually here fetching is nothing but based on the address, whatever the contents of there in that particular memory location or a register and all. So they are available all the time. They are available all the time. Only they are available all the time. And so therefore, for the next stage, we'll take the contents of this one there. They are from beginning itself, they are available. So whatever is there at the end, so that will be used for the next stage and all. That will be used for the next. We'll see that how this happens and all, like by using some registers will be placed. So with that, at the end of the cycle, these contents, whatever is there, will be right into that register, and that register will be read by the those things will be read by the correspond the next stage and all. We'll see that. Don't worry about that. Here, the things that were shaded here, just to show that usually the red part, the reading part of the information that is indicated by shading the later part of the time, because this entire activity is done in one clock cycle. For example, the later half of the clock cycle is shown as the reading the content, whereas the first half of the clock cycle is used for writing part and all. It means that suppose if you want to write something at the clock edge, or you can able to start writing the into the register or into the memory device and all. So therefore, here the writing part will be done in the first half, and the reading will be done throughout. So, but here finally, whatever you are reading at the end, so that will be passed to the next stage and all. So for that purpose, in case of reading, the shading is done at the later half, whereas writing, it will be done at the beginning of the clock itself. So therefore, you should notice the shading of the reading and writing the contents. Writing is the first half, and the reading has been done at the second half and all. And anyway, execution and all, there's nothing here. It will be done whole time and all. So that way. So here, what I mean to say is that in these particular 2 instructions here, so here, as per the first instruction, it completes writing only in the write back stage at this stage, right? But the next instruction, if it starts from here immediately soon after this, it means that when the first instruction go to the second stage, now the second instruction starts here, IF stage, supposed to start here. And then afterwards, the instruction decoding will be done for the second stage. The next one, it requires the execution. The execution stage will be there, right? So for its execution, S0 is required. but S0 is not available at this point because S0 is available only here at this point of a time. So therefore here to get this one properly, so what you need to do is that actually you had to stop fetching the further instructions. That means that you need to stall the pipeline. You need to stall the pipeline for this one to execute these two statements. One way is that actually because the content of here, the write back content of this one is required by the execution stage of the next instruction. So if you properly align these two execution stages and all, so if this happens this way, then you have then these two instructions will be executed smoothly, right? So for doing that, what happens here? That means that the second instruction, the sub instruction, the subtract instruction should not be started immediately, should not be started soon after the add instruction and all. It has to wait two stages, or you can say the pipeline stages time and all. Then it has to start. So when you start at this point of a time, right? So then you can have the properly that the execution stage where whatever the operands that are required, so those are available here, and from that it will take that and it will perform the subtraction operation and all. So for doing that, what I'm saying is that here in these two stages, that means it's supposed to start actually from here, but we are waiting, we are postponing this the activity of or feeding the subtraction instruction after two stages and all. So during these two stages, actually the bubbles will be introduced. Bubbles means we are not fetching anything at all. So therefore, the no activity. So the bubble will be first raised here. It's supposed to start here. The IF of this one should start here. Since we are not doing that one, so the no activity. So the bubble will be raised here. The bubble is no activity at all. And the same bubble will be percolated to all the pipeline stages, and finally it will come out and all. So that way, this is known to be data hazard. So one way to performing the right operation or without any errors means, one way is that whenever you notice this kind of anomaly or this kind of a problem, like the second instruction depends on the outcome of the first instruction. At that time, you have to see that actually how many stages you have to wait so that you can able to delay the instruction. So that many stages, and then you start fetch the corresponding instruction so that it takes care of that. So this is one way to handle the data hazards. But with this, what happens? The pipeline introduces the stalls and all. That means there will be delay. That the pipeline is not going smoothly. Like the instructions are not moving like one after another and all. There are intermediate bubbles are there. So with that, the delay will be the performance will be decreased. Suppose, for example, if you have such hazards there about 20% of the time, for example. So for every time you are leaving the two spaces, two bubbles for every instruction and all, for every dependency. So that hampers a lot the performance and all. So we need to see that the number of stalls that to be introduced or bubbles to be introduced should be as minimum as possible and all. So the other way of overcoming these data hazards will be using the forwarding principle. So in the case of forwarding, the idea here is that there is a dependency, right? That means the execution stage of the next instruction requires the outcome of the previous instruction. So if you place these two instructions properly, as per the correct pipelining, it means that the first instruction starts here, the second instruction starts from here in the next pipeline here starts from here. But here, the second instruction requires the execution on the operands of like S0 and T3, but S0 is available here as strictly speaking. It has to derive the operand from the register file, and the register file contents will be available only at this stage, right? But suppose already the instruction is feeded here, and at this stage we require the contents, we require the outcome of this one, we require the S0. But that S0 is available here, but S0 is computed by the previous instruction, but that is available here, right? But that has to be properly write back into the register, then it has to be given as per the normal procedure. But here, since it is already available here, that is a stage before, and here now at this stage, this instruction requires this output and all. But this is already available, right? Because this stage is just one stage behind this one. So therefore, in the previous stage, the add instruction already computed this S0 that is available here as output, but that is not written into the register. So, but it is available. That is available, and that is required for the next instruction, subtract instruction, as one of the inputs and all. So in that case, instead of we can pass this one as per the normal instruction, do that. And we can also bypass this. You can also like you can forward this output directly to the next stage, directly to the next instruction. Can forward the output by using some additional hardware. You can directly forward these to the next execution stage, the next instruction execution stage. It is nothing but actually here, suppose this is the stage where this stage is visited by sequence of instructions. After the first instruction left this stage, again the outcome is again required by the input of the same stage for the next instruction. So that's what we are doing here. But here, with respect to time, when you are showing here, the output is already available. So therefore, that has to be fed to the input to the execution unit or ALU for the next instruction and all. So that way, if you do that, then there won't be any stalls or any bubbles are required to fill up the pipeline and all. So this is one way to overcome the stalls. And in this particular case, but it's not that always the forwarding will help. And to some extent, the forwarding will avoid the stalls so that the performance will be not hampered much. But there are certain sequences, certain dependencies where the forwarding will not help at all. Right? We'll see that in the following classes. We'll see that. So we'll stop here at this point, and those who are the next class, you may leave. Right? Okay. Thank you.